It's my privilege to introduce our keynote speaker, Professor Mengjia from MIT. Professor Yan is an assistant professor in the ECS department at MIT. She received her PhD from University of Illinois. Her research interest lies in the intersection between computer architecture and hardware security. She has received the NSF Career Award, ACM TCCA Outstanding Dissertation Award Honorable Mention, and multiple micro topics in computer architecture, and also a Best Paper Award from Micro. You may have noticed her recent work on PACMAN that identified the hardware vulnerability in Apple's M1 chip has been widely covered by media. So today she's going to talk about looking beyond microarchitectural level side channels. So please join me to welcome Professor Mengjia for today's keynote.
Thanks a lot for the introduction. I will start sharing my screen. Does it work?
Yes.
Great. It is really a great pleasure for me to give this talk. As many of you, if you know me, you must know that I have been working on microarchitecture side channels throughout my PhD. I have been doing some attacks and defenses. So I find this is really a great opportunity for me to share just some humble opinions about how to move forward with this line of research. I think many of you, no one will disagree that even though microarchitecture side channels was discovered, studied, and defended for more than 2 decades, but it is around 2018 when Meltdown and Spectre were discovered, and then the problem of microarchitecture attacks were put into the spotlight, and we received a huge media coverage, and a huge amount of people were started getting interested in this research problem. Because I think there are multiple reasons. And maybe one of the reasons is that these Meltdown and Spectre attacks, they really break the abstraction between hardware and software. And since the problem is fundamental, it is really difficult to fix. And it kind of challenged a lot of design principles of computer architects, which we have been used for many decades. And another reason potentially is that we find that we actually do not know well enough about the computer architects that we have been designing for years. So it's like, I like this analogy of the iceberg, where caches, memories are more like the tip of iceberg. And it turns out that Intel, AMD, all these companies put so many details, corner cases into this microarchitecture that we were not aware of. And these microarchitecture design details, any of them could introduce security vulnerabilities. And we just in a battlefield that we do not know how to defend against them. So I've seen that in the last few years, we have a lot of efforts trying to find all these vulnerabilities, and we keep going deeper and deeper. For example, in the early work, we find L1, L2 caches are vulnerable to side channels. And then it takes not some time for us to see that lots of cache can also be attacked in a specific way. And then people realize that row buffer in the DRAM is just another type of cache. And very soon we are not very satisfied with finding bugs, finding vulnerabilities in caches, and we start finding vulnerability in some other more subtle data microarchitecture structures, such as the port contention in SMT cores and the network on chip, the mesh interconnects. And again, very soon the iteration becomes very fast. After just a few years, maybe less than 2 years, we are not even satisfied with finding vulnerabilities at digital level, like the recent work Herzbleed. They find at analog level, the circuit transition can introduce some power changes and can also introduce timing side channels. So I can see the trend of the whole research community. We are keep going deeper and deeper, and it's great. We find a lot of valuable vulnerabilities. It turns out in this microarchitecture structure, almost any microarchitecture structures has been demonstrated can be used to build side channels, row hammer attacks to affect the integrity of privacy of our system. However, what I want to say here is that it's great that we explore this domain and find the bottom of the iceberg, but maybe microarchitecture sidechain is not the only iceberg. In the whole research field, we have many other icebergs like side channels via software resources, memory corruption vulnerabilities, and many others. These problems has also been studied in other fields, and who knows whether they have some connections with what the problem we are currently looking into, the microarchitecture side channel. So this talk is a cautionary tale that I want to point out some limitations if we are only looking at microarchitecture only side channels by narrowing ourselves in this single iceberg. So my sense is that if we only look at the microarchitecture side channels, we may lose some other targets in the field. And in that sense, we may not be able to design comprehensive defense mechanisms. So the talk will consist two parts. The first part is saying that if we only consider microarchitecture side channel only side channels, we may miss some new threats arise from compound threat models. And I will use the PACMAN attack as a demonstrating example. And the second part will be about that even if we make some attacks work properly and we know the attack works, if we only think about the microarchitecture, we may misunderstand the root cause of this attack. So I will start the first part. So it used to be that people only we define threat models properly and then explore each threat model, find attacks and design defenses. Usually we consider software and hardware in isolation. For example, memory corruption attacks, such as buffer overflows, use after freeze. The community have been studied for maybe 30 years, more than 30 years, and come up with all sorts of defense mechanisms. And on the other hand, microarchitectural attacks, we kind of such as side channels, etc. We usually think that they are kind of in disjoint threat model. Well, what we find is that if you only look at them in this disjoint threat model, you may miss some new threats. And the PACMAN attack, our recent work, is just a very clear example. So let me just make sure we are all on the same page. A very short introduction to buffer overflow. Let's say this is your memory where you have a couple buffers and there is a function pointer just to sit next to your buffer. A very common thing happening in software community, software security is that a user forgets a bounds check and they do a string copy from a attacker controlled string, and that attacker controlled string is much longer than the buffer size. And after this copy, we have this buffer overflow, and the function pointer will be overwritten by the attacker, and attacker will be able to diverge the control flow to anywhere in the victim's address space. So we have a successful control flow hijacking attack. The attacker will be able to execute arbitrary code in the victim space, which is obviously not good. A very classical problem studied for more than 30 years in the community, and the people are seeking for solutions that can give you security and also low performance overhead. And then recently, not that recent, maybe 5 years ago, ARM proposed this ARM pointer authentication feature that can very efficiently block control flow hijacking attack. The idea is really that you have 64-bit address space, but our virtual address space is only 48 bits. So you actually have 16 bits as the higher part that is not used. So how about we reuse it for security? Then what ARM said, let's perform some crypto computation on the pointer and some sort and some secret key which are not accessible by the users. This will compute a message authentication code or a hash. And in ARM's terminology, it is called PAC. So you put this PAC, which can be used to verify the identity, the integrity of the pointer into the higher 16 bits. In that sense, if an attacker modified the pointer, it should also modify the PAC. So let's put this together. They also introduced two operations. The first is sign, where if you are trying to save the pointer into the memory, you need to compute the PAC and store it at higher bits. And you also need to verify it in the sense that if you are trying to use the pointer, you need to recheck the PAC by recomputing the PAC and compare whether the PAC matches the one stored in the higher bits. So let's put this together with the buffer overflow problem we have so far. Now you have a function pointer with a PAC at the higher bits. When the buffer overflow happens, the attacker will override both the function pointer and the PAC. Now, if the PAC does not match the function pointer, the program will crash. So it's a fairly effective defense mechanism with very low storage overhead and a low performance overhead. And it can help you to convert a successful control flow hijacking attack into a program crash. So will not leak data, etc. It's such a useful primitive, and the academia is already extending a lot. So there are already a lot of work trying to extend PAC for various purposes, such as to provide temporal safety, to provide like bounce check, like memory safety, etc. Also protect data on the heap and stack. Well, all these security mechanisms together with the PAC feature itself has been only examined under the memory safety threat model. And our PACMAN attack kind of try to say there's some other paths you can go around. So if you look at the threat model here, what I discussed so far is that if you have a memory corruption vulnerability, you can take it into a control flow hijacking attack. And the PAC will sit in the middle as the last line of defense for software attacks. Well, PACMAN will bypass this defense using microarchitecture attacks. And that is where considering a compound threat model will become valuable. To summarize, the key insight we have is to break PAC use microarchitecture attacks. And how do we do that? We first guess a PAC value speculatively to prevent crash, because if you just try a PAC value, you will crash the program. Now we will try it speculatively, and the nice feature of spec execution is that it can suppress crash. And then after this, we'll leak the verification results via a side channel, the classical side channel. It could be any side channel using caches, TLDs, or memories, etc. I know everyone potentially also knows spec execution, but just to revisit a little bit, spec execution means that instead of in-order execute instructions, we will execute instructions out of order. Like if we have a branch and 2 instructions, we'll make a prediction whether the branch is taken or not, and we'll execute instructions ahead of time. And if the prediction is wrong, we will squash these 2 instructions, roll back the processor states. However, we will not roll back many microarchitecture side effects. And these microarchitecture side effects can be used to leak information. And we will use spec execution to execute something we call PACMAN gadgets. These gadgets is very simple. If you look at it, it contains a branch instruction with a condition that can be controlled by the attacker. It has an authentication instruction which performs the verification operation of the PAC. If the PAC is correct, it will generate a valid pointer. Otherwise, it will generate an invalid pointer. And then it's followed by a load instruction that uses the verified pointer as an argument. So what we'll do is that if we run this piece of gadget during speculation and consider the following 2 cases, if the PAC is correct or if the PAC is incorrect. When we do the misprediction, we'll create a speculation window. And if the PAC is correct, our authentication will be successful, otherwise it will fail. In the case that it's successful, we will load. When we speculatively execute the load instruction, it will speculatively load a valid pointer and leave side effects in our microarchitecture structures. And you can use all sorts of microarchitecture structure side channels to detect it. Well, in the case that the authentication fails, then our load will cause an exception. But this exception will be a speculative exception. And when the exception reaches head of ROB, oh no, it actually will not reach the head of ROB because the branch will squash everything. So it even does not have a chance to reach the head of ROB. So it will never be really introduce a real crash. So by distinguishing a single load versus a no load is something side channels pretty good at it. And you can use any side channel to plug into this place. So the high-level idea of PACMAN attack is actually quite straightforward or intuitive after my explanation. While everything is difficult in real world, especially while trying to attack the Apple M1 processor, because when we were designing the PACMAN attack, Apple M1 is the only processor, desktop processor on the market supports point authentication. Nowadays, Qualcomm and Samsung also announced that they may ship processors for this feature, but at that time, last year, they were not there yet. Turns out that it's actually quite challenging to attack Apple M1 processor for a couple of reasons. There is no documentation of their microarchitecture details, doesn't like Intel, which has been extensively explored, even though there are a lot of proprietary information, but you can still find so many information online. Apple was known to be closed source, known to be being obscure and try to not release things publicly. Another issue is that they even do not have a high resolution timer in the user space. So for people who are doing side channel attacks, you know that Intel offers RDTSC, RDTSCP, which can be easily accessed in the user space, and you can get very high resolution timer. But we do not have that in the Apple world. In addition to that, Mac OS, again, very difficult. It's a very difficult system to integrate attacks on, since it is not the standard Linux. It's actually a hybrid operating system with different features on that. So essentially, with these challenges in place, we had to reinvent a wheel. Even the timer, we need to reinvent it to make it work. And we also need to reverse engineer many microarchitecture details. So instead of bothering you with all the details, I will just show you one reverse engineering result. That is the TLB structures. And it turns out that Apple has two levels of TLB, the L1 DTLB and L2 DTLB, and we reverse engineered their associativity and their number of sets. And in addition to these two levels of TLB, they have an L1 instruction TLB, which are separated between user and the kernel. An interesting fact is that the L1 DTLB works as a backstore for the instruction TLB, which is kind of slightly different from what we used to understand how we design TLBs. But anyway, these kind of structures explained a lot of weird behaviors we have observed in Apple processors. And by looking at these structures, by following these structures, we are able to demonstrate TLB-based side channel attacks. And the TLB actually is easier to integrate our attack on because they use virtual address. So you do not need to go through the virtual physical address translation, make our life easier. Another thing is that their TLB seems to be used some like more straightforward replacement policy so that it can even amplify our signal. So just show you one piece of results. We create a PAC oracle. So what is PAC oracle? It is a mechanism for you to distinguish a correct PAC and an incorrect PAC. So what we did is that we run our PACMAN gadget speculatively, and we use the TLB side channel to detect the case where you have a speculative load or not. And we find if we use an incorrect PAC, we see almost no TLB misses because it's a prime probe attack. If we use a correct PAC, we see above almost 99% of time, we see above 5 TLB misses. And why it's 5 misses rather than just 1, because we actually only access 1 address. It's because of their replacement policy makes the signal being amplified. Okay, with this PACMAN, with this PAC oracle, attacker can brute force the PAC value because attack can just brute forcefully try all the possible PAC values to eventually find the correct one. And since the PAC only has 16 bits, it's actually very brute forceable. And we demonstrate that a toy example that we can do it within 5 minutes or so. So this is the part about PACMAN. And while we are working on this project, we realized that the most challenging part is not to figure out the idea to make the PACMAN attack work, actually is to work with this very difficult system. And in order to make all the future researchers' life easier, my student developed this PACMAN OS. It is a Rust-based bare metal hypervisor that can directly run on Apple M1 and should be on future Apple processors, ARM processors. And this bare metal system can allow you to arbitrarily read different registers and do some noiseless reverse engineering experiments. And we already released it for researchers. So if future people want to work on Apple processors, welcome to use that. In addition to that, my student also presented PACMAN at DEF CON, and he kind of spent even more time working on polish and make the attack proof of concept attack even more realistic. And we introduced a couple of tools like a PACMAN kit is kernel extension. It's very similar to a kernel module in Linux, a kernel extension to Mac OS to enable data transfers and some mechanisms between user and the kernel space. And the PACMAN patcher can pack Mac OS to allow user space to use a high resolution timer. We also have the PACMAN Finder. It is a tool for you to find the gadgets, the PACMAN gadgets I just shown that we can use to do the spike scanner attack in the Mac OS kernel. And we also have this PACMAN OS that you can run bare metal on Mac processor. So I think there's a lot of work on Intel processors, and it turns out that Mac OS, Apple are investing so much and building even more aggressive processors. So if people are really interested in this direction, feel free to use this tool. Everything is already open source, and you can find that on the pacmanattack.com website. To just summarize a bit, PACMAN is an attack that sits between these two threat models, explore these compound effects of threat models. And we actually find that PACMAN attack is not the only attack sit in the between of the threat models. People have been thinking about doing side channel attacks to bypass ASLR extensively, while most paper consider ASLR just a demonstration of side channel attacks, maybe because ASLR is easier to break in that sense. But this paper, speculative probing attack, which is published in CCS 2020, is one of the few attacks that I see that they bring these two attacks actually really together. You do the ASLR bypass and also use the bypass result to demonstrate the control flow hijacking attack, which I think could be a nice read if you are interested. To summarize, the first takeaway I want to give is really that new threats could arise from the compound threat models, and I would hope us to look broader into different threat models. Now let's jump into the second part. My second part is really want to talk about that with a very complex software and hardware system. We may think that when we make attack work, it's great, but many times we may misunderstood the root cause of attack because the systems are very complicated. If you just look at the tiny side channels we are having today, we are running two applications together in a processor, and they are sharing all sorts of resources, including CPUs, caches, DRAM, and software resources. And what we usually have is that the attacker will just profile the system to get some signal, and they use the signal to decode some secret from the victim. And many times, if the signal becomes really complicated and or include a lot of noise, we just tend to use machine learning, because machine learning is just so good at finding correlations between two things. And once you find a correlation between the signal and the victim's secret, you just make the attack work. The problem I want to point out is that with such a attack strategy, many times machine learning does not offer interruptibility. So you may not know the root cause of your attack. I want to just show one example, and this is the work published this year. This is a work published last year by a group of researchers doing cache occupancy attack. What they did here is really simple code, because they make the code run in JavaScript and very low resolution timer, where you have a loop, and here you have you record the starting of the timer, and you set the counter to 0, and you enter a while loop. And if you are within this 5 millisecond threshold, you just keep incremental counter each time after you finish sweeping a cache. And then you record the counter for every 5 milliseconds, and you collect a trace. So the idea is really that attacker and the victim are contending with each other in the cache. If the victim uses the cache, the attacker will take a longer time to sweep the cache, and it will increment the counter slower. And with that, they call it a cache occupancy attack. Obviously, if it's a cache occupancy attack, it should exploit the cache. So what they did is that they use the cache occupancy attack to demonstrate a website fingerprinting attack. So what you do in website fingerprinting attack is that you get a lot of websites and you get a lot of traces, and these traces were collected using the code in the last slide. And you train a machine learning model, neural network model. And this is what you do in the offline phase. And in the online phase, you will collect a trace with an unknown website. And then you consult this machine learning model, say which website it is, and it will tell you an answer. And hopefully this answer is correct. And what they show that the answer can be correct with 90% accuracy, so the attack works. Well, what we did is a relatively surprising experiment. That is, if it's a cache occupancy attack, it should exploit the cache. But what if we remove the cache? So we remove this line of code, the cache access pattern, the access behavior. Guess what? Should the accuracy of the attack increase or decrease? If it's a cache attack, we should not get too much signal because there are not any cache activity here. The accuracy should significantly decrease. Well, what surprised us is that this is our result. The blue bar is from our attack after removing the cache accesses. The accuracy actually increased in almost all the setup. We tried it on some different Linux different operating system, different browsers. They are consistently higher. For example, in Safari on macOS, we are even increased the accuracy from 73% to 97%. Now, it really caused us to think about what is the root cause, because obviously cache is not the root cause, otherwise the accuracy will decrease. And hopefully after our exploration in the next 10 minutes, I could convince you that machine learning assisted side channel attacks, they work as a black box, and it's actually challenging to find the root cause. And sometimes there exist multiple root causes, and it's very difficult to diagnose which root causes matter more. So how do we figure out the root cause? There doesn't actually exist a existing method. So what we do is that we go back to the classic, what we kind of used for like scientific research, where you see make some observation, you make some hypothesis, and you try to design some experiment to verify this hypothesis. And we analyze the data and see whether our hypothesis is correct, and we will go around circle by circle. So our first observation, as what we've seen so far, is that if you remove the memory accesses, we get like 95% accuracy. So our question is that what could cause the throughput to change over time? Because our instruction, our code above, which remove the memory access, is actually basically profiling the CPU throughput by doing the incrementing of instruction. So our first guess is actually maybe it is due to frequency scaling, because frequency scaling could affect how fast you can increment the counter, obviously. So what we do is that we just disable frequency scaling and repeat the experiment. Turns out that the accuracy we get is 94.2%. It's a marginal difference, only 1% difference. So we think, okay, little to no noise comes from frequency scaling. Then we need to repeat. And we will think about what else could cause this side channel to happen. And our next hypothesis is that maybe because of CPU core contention. Guess what? This Chrome and this web browser, they actually can create many threads, just occupying all the cores in our system. So it's very likely that attacker's thread and the victim's thread, they are contending with CPU resources. And when the attacker is not using the CPU resources, it just doesn't have the chance to increment the counter. And we repeat experiment by pinning the attacker and the victim into separate CPU cores. Guess what? The accuracy only dropped by 0.2%, almost no signal come from CPU core contention. We have to repeat, and our next hypothesis is interrupts. So just to make sure we are all on the same page, system interrupts are used to deal with asynchronous events. If you have some hardware I/O devices like network card, graphics card, and these I/O devices could generate interrupts to preempt our core. For example, here, both the victim and attacker are running in the user space. Let's say the victim issues a request to some hardware device. If you are rendering the website page, you may issue request to a network card, and you may want to display something, render images, etc. So you will need to use all these devices. And when the hardware devices is processing this request, these two processes can keep running. And when the hardware device responds, it will generate an interrupts. And the interrupts could go to any core actually in modern system. It will possibly go to the attacker's core, and then it will preempt the attacker, jump from the user space to the kernel space, and ask to the interrupt handler. And only after the interrupt handler being finished execution, then you go back to the user space and you can resume incrementing the counter. And the nice thing is that Linux operating system kernel, Linux actually offer you some interface to configure how to ping these interrupts, how to deliver these interrupts, but some are not, and we will talk about that later. So what we can do is that ping these interrupts to the cores that do not run our attacker, and we repeat the experiment. The accuracy does job. It drops about like 66%. It's already the biggest job we have seen so far. So we do think a lot of signals do come from these interrupts. But we also have to admit that there exists a lot of signals still underdiscovered. If we look at the interrupts in our system, and you can actually find this when you just look at this proc interrupts file in the Linux operating system. And we find that actually many interrupts related to this hardware I/O, they are called movable interrupts, which can be configured by the Linux. And these interrupts include the mouse, like interrupts generated by your mouse, keyboard, network card, and the graphics card. But there also exist a lot of interrupts that are not movable, such as timer interrupts and IRQ interrupts. So timer interrupts are essential for us to schedule processes on different cores, and this cannot be moved. Each core needs to have timer interrupts. IRQ interrupts is really, for some interrupts, it takes very long time to process. So the operating system will complete part of that and put the remaining into a queue, a software queue, and then opportunistically trigger the IRQ interrupt to process it, so that you will not preempt a process for too long time. Turns out these non-movable interrupts, as the name indicates, they are not movable. So, and they are necessary for the operating system to function, and they haven't been studied in prior side channel attacks. And because they are not movable, we actually cannot repeat the experiment anymore, because we do not have a system for us to do that. And we have, in that sense, we have to consult some other approaches. So what we did is that we do system instrumentation. So we really need to go deep and analyze the system and really see how the signal flow through the system. So what we did is that in the kernel space, we use eBPF to instrument Linux kernel at runtime. So eBPF allows us to put kprobe throughout the Linux kernel. And what we did is that we put it at the beginning, at the end of interrupt handlers, and we will use these probes to record the time we enter an interrupt handler and the time we exit an interrupt handler, so that we have a clear idea how much time we spent in interrupt handler. And the second, we modify our user space code to, it used to be a JavaScript code. Now we use it, we write it in Rust so that we have bare metal control, not any other random things. And we'll record time at the user space when I leave the user space and when I re-enter the user space. And we got a very nice, beautiful plot. Here, the x-axis is the time. So you can see things change over 15 seconds. And the y-axis, you have blue and black lines. The black line is the time we spent in the kernel, which is reported by our eBPF tool. And you can see that it varies from 0% and 55% of time you spend in the net kernel in interrupt handler. And the blue line is the counter value we incremented over during the user space. And you can find there is a correlation between them. Here, when the interrupt handler time increases, the counter value decreases. And here, and also here. And if you want to see things even more clearly, you can flip the blue line and you can see the correlation even better. Okay, and we also did more statistical analysis in addition to this visualization style stuff. We also did some statistical analysis, and we find that 99% of the gap that you find in the user space can be explained by the presence of interrupts. And there's still 1% of time that you cannot explain, mainly because the kprobe, there's some places you actually cannot put kprobes in. And my student also did some demos of our attack. You can, we have this, everything is open sourced, and you can find all this code the eBPF analysis tool and also the attack code on this website. This demo shows that you can actually do this attack in some normal machines. Here, we try to collect traces for Amazon, for three traces for Amazon, and we also collect 3 traces for weather.com. Make it speed up so we can see it faster. And you can see here that even though the Amazon traces are not precisely match each other, but there does exist some patterns that distinguishingly different from the patterns, the traces we collected for weather.com. And that is, you can see that in real time. In summary, this project actually tells us that there's always a bigger fish. It used to be the case that people think that process isolation, cache side channel attack is the fish after the process isolation. And we find in this project that within a very complex software and hardware system, interrupt side channels may be even tracing after you, and you are not sure where is the root cause if you just narrowly only think about microarchitecture side channels. Hope I already convinced you that it's essential for us to do comprehensive security analysis in complex software and hardware system. But I also want to mention that whether it is the end of story or not, I have to say that this paper we published in ISCA is not the end of story. There are a couple of things we cannot answer yet in that paper. First, that we actually did some experiments by put the attacker and the victim into 2 virtual machines and ping the virtual machines into different cores and also ping the interrupts properly. Guess what? Compared to the process isolation, we see the accuracy of our attack increase from 88% to 91%. And then this is very confusing because theoretically, virtual machine isolation should bring us more isolation. Well, what we observe is no, it actually increased accuracy. And we have some hypotheses, maybe because VM exits, when you handle interrupts, you have 2 levels of exit. One is inside the guest virtual machine. The other is the host operating system. But we do not have a good approach to verify that because the eBPF instrumentation also have some limitations. It's not able to handle virtualization environment yet. So we actually do not know why it is happening this way. It also makes things very difficult to decipher how the signals transfer between the machine learning model output. So far what we are doing is that when we see cache and interrupt played together, we observe an accuracy. And we remove the cache, only do the interrupts, we observe an accuracy again. And then we just are unable to play with the trick again by removing interrupts and just see how cache introduced the signal. Maybe the cache also introduced tons of signal, but we just cannot do these control variable experiments again. And because machine learning is a black box, we actually do not know which one can cause larger, stronger signal. And this may also involve how machine learning explanatory works. Finally, whether there exists a bigger fish or not is another question we cannot answer. My student present this paper at ISCA, and after the presentation, it kind of triggered a lot of discussions. Many people come to us and say, maybe it's because that, maybe it's because of the other reasons. And with such a constrained system, we actually cannot answer all these questions. So I hope that in the future, we could invest some efforts to build some mechanisms or instrumentation systematic analysis framework to help us to answer all these questions. Sometimes answering these questions may be even more important than making an attack work, because without understanding the root cause, we just do not know how to design efficient defense mechanism. So to summarize everything, I hope that this talk could inspire some ideas from you and can encourage you to look beyond microarchitecture-only side channels. In addition to going deeper, we also want to go wider and more horizontally. So in the very end of this talk, I really want to leverage this very valuable opportunity to just talk about these 5 lab assignments developed in the lab. So I know that in the last few years, the community about hardware security has been thriving, and a lot of people really want to jump on this topic. And it's great that we always want the community to become larger. And I got some questions from students about, okay, how can I start research on computer architecture security, and whether it is my cup of tea or not. So I think the best way to figure out how to start and whether it is your research interest or not is just get your hands dirty and try something. So we developed with my students, we developed these 5 lab assignments that all the things are designed as a capture the flag competition. So you are like working this as solving a puzzle. So people all like solving puzzles, right? So the first lab assignment is actually inherits from Chris Fletcher's that job lab, try to use cache side channels to build covert channels and side channels. And we kind of explore more and use design experiments for students to design Spectre attacks across kernel and user space. And we do the website fingerprinting attack, like what I described in the Bigger Fish project. And we will also guide the student to do the demo and also guide the student to figure out the root cause. And we also have a lab on row hammer attacks and also on how to use side channel to bypass address layout randomization, so that you see how the compound threat model can help us see more threats. Everything is open sourced, and we also provide a lot of support for instructors if you want to use that in your instruction. And thanks a lot. And I also want to thank all my students. They did all the work. Eventually, this is the summary, and thanks a lot for listening.
Thank you very much, Professor Yan. So now we have some time for the questions from the audience. Please use the reactions, raise your hand to ask questions, or you can enter your questions in the chat box. So is there any questions from the audience? Maybe let me start with some question first. We often know the security and performance are sort of contradictory in the process of design. And it's great to see your scientific method that you presented, peel the onions to figure out the implications of different architecture features to the security. And that is a very methodological method to understand the impacts of the microarchitecture or architecture features. So my question is basically, what is your advice to the people, to the architects who are designing microprocessor or system in industries? How do they take, security vulnerability into account in a more systematic way, so they can, design a countermeasure in advance before people can exploit the system?
Great. It's quite a difficult question. So a funny anecdote that when I present, my students present the Bigger Fish project to some Intel folks, and they actually find the methodology we used to find the root cause of a side channel attack is very similar to some methodology they use to find some performance bottleneck. So they kind of share the story where there's a period of time that they find some people complained about some performance degradation, and they think, okay, that performance degradation must come from some prefetchers, whatever. And they did some analysis and turned off the prefetch, etc. And they find even if you turn off the prefetcher, it doesn't affect the performance degradation. So I would say that finding the root cause of side channels may share a lot of similarities as systematically find the performance bottleneck. And that may be a point where things can converge. And I think the community has been doing systematic analysis for performance for many, many years. We have accumulated a lot of experience. We want to delve very deep and try to monitor the raw activities in the system. And that is something we have a lot of experience. So I would hope that some of this experience could be leveraged also for security, actually. I think according to this project, the bottleneck we have is that we do know how to diagnose. We do want to play a lot of tricks to figure out the root cause, but especially when things going through in the middle between software and hardware, for example, interrupts. It's really stuff sit between the software and hardware. They are kind of a co-design mechanism. Then the things we can play is very limited, and we kind of be constrained by the Linux kernel. And if we want to really isolate things, and we need to change the Linux kernel to isolate RQ work interrupts, that would be even a design project for a whole year. So I think in that sense, if we can build an ecosystem for convenient diagnose these root causes, maybe this ecosystem can be used both for performance and security. I think peeling onion is something that we're already doing. So that may be a change, a potential research direction we can explore.
Okay. Okay, so we got a couple questions from the chat box. Let me read it out for everyone. The first one is from Biswa. He's asking, for website fingerprinting, is it the usage of JavaScript that is contributing to the memory grams?
Good point. So JavaScript, so we find that actually JavaScript is very difficult to analyze. I think if I interpret your question correctly, is that even if we remove the cache access pseudocode in the pseudocode, you may not completely remove all the cache accesses because JavaScript itself is so complicated. Who knows what is done in the background? So you may still have some like cache activities. I agree. I think that is something we do not know clearly. That's why later when we do the detailed instrumentation attack, we actually change it to the Rust code so that we have the bare metal control. And that also collided with the question I actually posed after like end of story. Is this end of story? I think it's not end of story because in some cases we remove the cache part. So we know the interrupts can cause the accuracy to increase. It can contribute to the signal, but we cannot do the experiment of removing the interrupts and only putting the cache there. I can bet that the cache does introduce some signal. And I really agree that the cache activities of websites do introduce signal, but how much that signal is like without interrupts interacting with it is something I cannot answer. So I do not know the answer in that sense.
All right. Okay, we have a second question from Pavlos. Thank you for the great presentation. His question is, PACMAN is another transient attack. Do you believe that we should focus on efficient ways of mitigating it or include it in the general ways of mitigating speculative side channels? So basically he's saying the PAC authentication is a single instruction, is not so often in workloads. So a dedicated mitigation will be much more efficient than general transient mitigations that focus on load instructions. So what do you think about, should we focus on the more efficient ways or should we include it in the more general ways?
I think my answer maybe not that academic in the sense that I would say both need to be explored in terms, depends on how secure a system should be. I would say we have seen so much exploration in the past 30 years on how to secure our memory, how to adjust the memory corruption vulnerabilities, but very few defense mechanisms are actually implemented. And you can see the mechanisms that are actually implemented in industry. They are not complete solution, many of them. If you are trying to do complete solution, potentially we should go cherry because they kind of offer all the flexibility and the most academically beautiful work. Why PAC was used, even though PAC is not really a complete solution in the sense that PAC doesn't offer many other security features than cherry, is because it has low performance overhead and it's simple. It has low complexity, etc. It requires the minimal changes of your software and hardware. So all these aspects need to be considered. So my answer would be, we should keep exploring general defense mechanisms, but also on the other hand, if your system is really have such a critical trade-off between security and performance, some point solutions could be very useful in the sense that for PAC authentication, it is very critical for system to be secure, to be secured from control flow hijacking attack. And with being known that PACMAN attack exists, you can propose very targeted solutions. So actually, after PACMAN was released, ARM has already have a very nice document in their website about how to mitigate PACMAN attacks. And their solution turns out that you do not need to introduce a lot of fancy hardware features. They actually have two versions of PAC. One version, I think that is the version we explored in M1, and the other version actually can fault an instruction at the verification stage. It will even not generate the fault when you use the instruction. It will already generate the fault when you do the authentication. And they said that feature can be reused with some code changes to already secure the processors without introducing new hardware. So I would say both mindsets is useful. I would say the community could explore both directions. There exist pros and cons. There's no consistent better metric between one versus another. And I personally actually enjoy thinking about general comprehensive defenses because it is very nice brain exercise, because even though I know that the possibility for such general comprehensive high overhead mechanism being implemented in industry is a bit lower, but I just enjoy this like brain exercises a lot with my students. On the other hand, I also want to do this like point solutions, even though I know it's not that academically elegant, but I know they are so practical, right? So you sometimes cannot have the both of the world.
Mm-hmm. I think a lot of people will be interested in knowing that if Apple or ARM have any official response to the PACMAN after it was published.
Responsible, I think the community has already starting.
Their responses or reactions to PACMAN. Did they make any
their
official
reactions? So yeah. So I would say Apple seems to be very calm in the sense that the reason they are being very calm, I also understand that, as I mentioned, that PACMAN attack is breaking the last line of defense. So PAC is really sit as the last line of defense. You need to have a vulnerability and you need to know how to diverge this vulnerability into a control flow hijacking attack. Then PACMAN will block the last step. So what we are doing here is really just to block the last line of defense. There already exist many other defense ahead of us. And also it's a very challenging attack to pull off. I have to admit that it's a very challenging attack to pull off. It's much more difficult than a plain Spectre attack you can easily pull off in a modern system. So they are much calmer and they think they do have other features can secure their system. And I think hopefully in the future they will address this hardware feature, hardware vulnerability, because it's not too difficult to fix it. ARM seems to take it more responsible, and they even have such a long article to discuss how to deal with that. Mm-hmm. So I think I do like ARM's responses in the sense that their response is includes a defense mechanism that I haven't thought of. So their software hardware code defense mechanism is a nice trick, and I like it. So that's it.
Okay. Do we have any other questions from the audience? All right. I guess we are right on time. Thank you very much again, Professor Yan. And I'm going to pass the microphone back to Omer. Thank you.